only for the considerations of 1, 0, and 0, 1, right? In the other conditions, it's false, it's the off condition. So how do we create a linearization for that class, or for that particular output? How do I know that is a function, right? I can argue that that is a function, because it has definite input and categorical output, but I know that it's not a function that I can model at a strict linear level. So the understanding of how this function actually operates, I said previously that I should be able to construct a version of a function with some non-zero level of error for any version of a function. So I should be able to build one for the exclusive OR. However, I cannot do it with one neuron, right? As a matter of fact, even if I increase the number of neurons here, I'm not actually going to be able to create a true operation, full operation for this system unless I get really pretty lucky with the way in which the system converges, right? So no single neuron will actually be able to model this system. Now, I said I can width it, I can put more neurons together, right, on the width of the system. And the more neurons I put together, possibly the better the surface will get with respect to describing the regions. Right, so at 3 neurons, I wasn't really getting anywhere. Probably the ideal consideration might be somewhere in the neighborhood of about 4 neurons. Okay, why does this work?
It kind of breaks it up into quadrants.
How is that describing, and that describing, and that describing this? That's the portion that breaks your brain a little bit.
Yeah.
All right, because the features that are being extracted here, notice they're coming from the input features.
Right.
So the input features are already processed in source, meaning that that feature already exists. So I have a two-dimensional feature. I have x, y, effectively. So I have x1, x2. I'm calling those the feature correlations with respect to the system. So each individual position, each individual value on that graph has an x1 and x2 coordinate. Effectively what I'm saying is my first input is distribution with respect to x, distribution with respect to y, right? And those are being fed in through this system weights. They're going to create their understanding of a division of a surface. Notice, that actually kind of makes sense for a cluster in the upper quadrant, right? And this one down here kind of makes sense for a cluster in the lower quadrant. That starts to make a little bit of inference, a little better inference. But notice what's happening here. Well, it might define the lower boundary for the 1, 0 quadrant, right? The bottom left quadrant. It might sort of define the lower boundary, but it's not exactly correct. It's offset some way. Also, it might define the upper or center quadrant for the upper boundary. Still not quite right. But notice what's happening here. All these values are being reconfigured and reweighted. They're being rescaled by a weight parameter. So these are features. These themselves, these individual elements, are in fact features that are being extracted from previous features. So the sequence in a neural network works by extracting features of relevance, right? Finding a pattern, and utilizing that pattern as the output for that neuron in the subsequent layer. So the inputs of any given layer are taken from the previous layer in the system. We can look at those as features no matter where they come from. Remember I was talking to you about how effectively one set of leaves become the place where the roots for the next neuron interface with each other? That is where this system gets passed off. The outputs of one neuron become the inputs of the subsequent neurons in the system. So if I wanted to try to create something more complex, I actually don't need anything really crazy until I get up to this level, all right? Let's see what happens within the system. I noted that I was actually able to create something relatively quickly, like within a matter of about 100-ish epochs, I should be able to get to something that works relatively well. But notice what happens. What happened to the training loss? Training loss zeroed out, right? But the testing loss isn't. So let's look at the test data. The test data isn't zeroing out because there are some distributional characteristics that are at play that are warping our understanding of the data space, right? This specific selection of training data doesn't take into consideration the placements of some key items in the system. Notice down here, all of my training samples that don't have a all my testing samples that don't have a corresponding training sample, right? There's no local version of those with respect to the testing. So when the system attempts to converge on a solution, given this parameterization, what's happening? It's not getting a good solution to this process. And we're going to notice that I continue to train this process, what's going to happen. Additional overfit. We see already that those two training lines have started to relatively diverge from one another. I haven't gotten to a point where I have started to have ascending test error, right? I haven't started to increase test error as a result of decreasing training error. This is the interesting part of it. Some neural networks, depending on configuration, may actually converge to a stable testing loss and then continue to be able to be trained without losing additional testing loss. It doesn't necessarily guarantee anything about the quality of the model output because there is still a degree of flexibility at play here that may not necessarily be learning additional information about the underlying process. It might not be modeling the full, robust, and generalizable understanding of the system, but it might be making special exemptions and special rules for that training data anyway. That's still very possible. I said there's a lot of free parameters in these systems. As a result, it's very difficult to get a true picture of it. So we said this one was fairly easy, right? Did we look at the circle one? Yeah, the circle one's nice because all I really need is about 4 neurons in order to create something that looks kind of like a little triangular circle, all right? Triangle corners on it. I increase the number and I increase the relative smoothness of the transition and the shape. Each one of those, I think you can see fairly easily when we're looking at the edges, each one of these is effectively corresponding to one of the surfaces expressed by each of these linearities, right? Now, what happens if I increase the number of hidden layers? Currently, I have 2 feature inputs, 6 neurons, so this network is what's traditionally considered wide, right? It's wider than it is deep. So it's not necessarily passing, it's creating a lot of different reference images, it's creating a lot of different perspectives on it. You can think about it from the idea that it's effectively rotating its perspective, its value input, and reweighting the system based upon a variety of different angles of the system. The hope would be, because each one of these is a linearity, right? So effectively it's looking at it as a surface transition. So I'm saying it's each one of those effectively be attempting to do what? Create a linear transposition like the LDA. So you remember LDA does that rotational transform? Each one of these is a type of LDA, in effect, right? Looking at it from a slightly different angle. You can see each of the angles that it's trying to determine where it starts and stops with respect to the reflections. Notice though, it's still got this rigidity to it, this squareness to it. So what's going to happen whenever I start adding some noise to the system? If I have some noise that starts to overlap the data samples, the system is going to have a little bit harder time finding an ideal output. Notice it's gone back to that weird triangular shape, and it's trying somehow to capture some informational variance with respect to that testing data somewhere in the center. Why did that happen? Well, because there isn't quite as easily reducible error characteristic with respect to this now mixed together data. Neural networks work really, really well for data that's well separated, all right? Similarly to how LDA can be said to work well for data that's well separated, because you can maximize the placement of the border of separation between the elements in that particular case. We're also going to look at another process that has a similar objective function in that respect called a support vector machine that accomplishes a similar process for separating surfaces utilizing a different trick, right? So our trick right now is to recombine the linearities. The trick we'll be utilizing in the future will be to dimensionally project this to a higher dimensional space and then redivide the surface area. Notice, I've had a divergence. I have experienced the divergence. Testing loss is going up. Testing loss is slowly going up. What's happening here? I've overfit. Obviously overfit. I waited to mention it until it got big enough where we could see it easily. Okay? So this one is not going to be solvable with just additional neuron layers. Can I do it with fewer? Actually, fewer neurons is likely going to converge to a better output in this case. Why? Uh-oh, we're diverging again. We overfit. We gotta stop early before it gets any worse, okay? That's actually a technique we utilize, is that once the divergence starts, once we've hit a maximum with respect to a balance between testing and training data, we can stop the model training. Thus, it won't adapt any further. Thus, it won't be able to memorize the additional data. How does it do that? Well, it doesn't see all the data at once, right? This is another cool feature of how neural networks are trained. I don't have to show it all the samples at once. Let's say I have 1,000 samples. I can show it 100 of them. I can then have it adapt to those 100, all right? Then show it 100 different ones, go through the forward process and then the back process and update the model based on that mechanism, right?
So it's got like a built-in validation.
It has a adaptive methodology, right, where it can't see all of the data points at once. We actually can even utilize a mechanism by which we call procedural masking, yes?
Are there situations where you don't want to early stop? Because I usually always add early stopping.
No.
Not early? Okay.
Never. I've never seen anybody that would make an argument that a intentional overfit model is a good thing. There are ways in which you can utilize overfitting characteristics to make inferences about the data characterization, but that's similar to the concept of a bootstrap, right? You're not really using the model as a learning framework, you're utilizing it as attempts to do some sort of parsimonious extraction of data variance. So you say, what happens, what's the difference between the training set and the test set in terms of performance? You can effectively look at the curves and see when did the model start to overfit, right? The rate of overfitting with respect to the parameterization of the system might imply that the relative degree of complexity of the model, either the layer number or node number characteristics within the layer, if you're adjusting those like you do with the parameterization in k-fold, what you might end up with is sort of a prime number, right? The prime minimization with where you're able to start and stop. So the slower the rate of divergence, effectively the argument would be that you're getting closer and closer to the best version of the neural network model from a structural interface perspective to be able to characterize that particular set of data, right? But the argument goes away a little bit whenever you think about it from the perspective of like persistent training. Could you get to a model that would be exactly the correct complexity such that you could keep training it and never have to stop? Okay, I'm talking about something, probably you're doing deep learning, right?
Yeah.
Okay, so talking about something that's beyond the scope of this class, but I figured I would indulge you for a moment. So we note a couple of things about what we're actually looking at within the framework of a standard vectorized model, right? So let's go back to thinking about how this system actually works under the hood. We saw what it can do. It looks pretty powerful. It's nice because one of the things is we've always had a challenge on understanding with a lot of the other topics and methodologies we've utilized is visualization isn't exactly their strong suit, right? So having a tool where I can go to a website and show you guys exactly how this thing works on a moment-to-moment basis, I think is a really good tool for understanding how it operates. The other thing I think that is nice about it is we like to have models that tend or seem to work the way we work. We think about intelligence from the perspective of saying that humans are, so we utilize a bit of a logical fallacy, right? That logical fallacy is we want to find something that is intelligent. So we go and we look at humans are intelligent. So we say humans think in this way. So then we make an argument for a characterization that would say this. If it thinks like a human and it seems to have a form of intelligence, then it is in fact intelligent, right? We're actually making a kind of prompt or hoc kind of logical fallacy of saying if it thinks like us and it seems to solve the problem, then it must be intelligent because human equal intelligent, right? But it's kind of a human swim in ocean, fish swim in ocean, human equals fish kind of perspective, right? That's not exactly true. The argument here is between two schools of thought with respect to intelligence. One is the Carnegie Mellon school that talks about like hard AI or strong AI, right? And the other one is sort of the MIT slash inherited institute, or what is it, MIS, I guess it is. But MIT original constructs dealt with something called weak AI, right? So what is weak and strong? What's the difference between them? Weak AI solves the problem, but doesn't necessarily have to solve it in a way that we can explain it, right? It doesn't have to explain to us. It goes, I don't have to impress you, right? It says, I don't have to validate myself to you. Here's the answer. Just shut up, take it, you know? And it's like, I have no idea what happened here, okay? So we're gonna look at a couple of what happened here moments as we get further and further in the system, especially when we get into convolution. So I wanna go through this kind of quick. I know we're not gonna get into the level of detail that everybody might love to have here, but one of the things that I say is, as we know how linearities work, I'm gonna kind of skip forward a few steps relatively quick for us, because I think you can parse out what's happening here. So this process takes the initial linearized vector through an array of weights. Those array of weights output via first an integration, then a differentiation, right? You have the summation characteristic and then a sigmoid, or we use the sigmoid as the operation or activation operator, right? This system then feeds into some operation called a softmax, which it takes the output of the hidden layer, the layer in between the system, and converts it into a probability estimate for the multiple classes of targets we have. How does that work, probability estimate? It's similar to a maximization of a optimizer function or an activation function, right? So it is going to take the max of the activation function for each of those class output characteristics. The training process of a neural network, we've seen in action, but what does it actually look like under the hood in terms of the mechanism for optimization? At each step of the process, we're going to call those epochs or iterations, right? There's a control system diagram. Everybody's seen standard control system diagram, right? So I'm redrawing this as a control interface. X of I, this is my input interface. I have a weight and bias infrastructure. This is the array-driven system. And then I have some output y sub I that is effectively my inference target. Normally that's where we put a hat on it, okay? The reason why I say we put a hat on it is because it's a guess estimate based upon X sub I's inputs, the feature input, and then W for the matrix of input arrays, plus the bias characteristics. I'm going to get y sub I, and I'm going to use, instead of yi for the actual target, I'm going to use di, right? Di. That's actually the intended designated target, right? So designated target and y as the output of f of x, treating the network and every element within the network effectively as a function. So we know each individual neuron within the network is a function, operates as a function for this decision making. So we say, I'm going to look at all the processes together, I'm going to compare them to the output characteristics, and then I'm either going to have some output perspective that is going to be either above or below d sub I, right? So d sub I minus y sub I is going to be my error characteristic. That's y minus y hat for all of us doing the game at home, right? So error goes into another functional operation, and we use that error to adjust the parameters. We've been doing this thus far, right? But how did we utilize the error to adjust the parameterization? Well, we only had one weight in a standard linear space. So we could assume that all of the error that we were experiencing or seeing within that system was a result of that one weight, right? So how do I get to a space where I can make an argument how to adjust multiple weights, because I know each of the weights has some participation in the error, right? I have to spread the blame around. So the mechanism by which I change the parameters is a mechanism by which I adjust the weights of each of the linear assumptions of each of the perceptrons in order to be able to optimize given some objective function, right? So normally we're utilizing something like a mean squared error, or residual sum of squared error, or we have other mechanisms for adjustment, such as classification errors, right? We'll be looking at incorrect classes, distance metrics. So if I utilize a softmax instead of a hard binary output, now I can look at the difference between my estimate of probability and the true probability of the system, and I can use a distance-based metric in however dimensions, on how many dimensions I'm interested in. And I can either do Euclidean distance for standard planar transforms, or I can do something crazy, right, like Bobnik-Chernovich distance or Mahalanobis distance in order to measure the difference between my output and the target, right? You guys have never seen what those look like. Mahalanobis distance is how you measure the difference for distance transit, like driving around a city, right? You can't drive through a building. There's no direct diagonal. So you have to go around based upon the distance characteristic. And a BC dimension is a projection in non-Euclidean geometric space for distances between elements in high dimensionality, right? What's the distance between the output and the target whenever you have an 8 or 10 dimensional space, right? So it's a mechanism for solving that higher level problem. We remember looking at these as a basic construct for gradient surface mechanism, right? We talked about this with respect to basic stochastic gradient descent, right? We talked about this in structure. I often don't remember exactly what I've discussed with everybody because I teach this same module in like 3 of my classes. So, and I'm doing it all at different times right now. And lately I've been doing it kind of all together. So it's been really weird. But the gradient descent process utilizes this idea of maximization of vector projections based upon the Jacobian of the surface, all right? So we use that symbol grad, which is the inverted delta, to indicate J, which that grad J is the value when calculated as a surface tangential to the external error surface of, hold on, I have another version of it that looks a little better at it. Hold on a second. Come on, why different slides? Okay, I'll go back in a minute. The surface calculated by the gradient effectively will always return, no matter the dimensions, it will always determine the orientation of a surface set on the instantaneous interface, right? The tangent of that surface pointing in or adding to the direction of steepest ascent, okay? Direction of steepest ascent. So the output of that gradient function will provide for us whichever way the surface goes most upwards, right? So we said we liked that to a certain extent in some spaces, right? But we don't want it with respect to an error surface, right? So if J returns as gradient the direction of steepest ascent, and the value of this system in its horizontal space is the current weight of the system, right? So we have the gradient changing, right? This is the error. The error surface. We start with high error, right? And then as the weight changes from the initial position to some ideal position in the center, we're going to make an initial step, which is going to say that the gradient surface is going to point where? It points back in this direction. The true gradient is going to point back at this point because of what? It's going to say that if you decrease the weight, the error is going to increase because it is the surface projected by the direction of greatest increase in relative error. So if I go the opposite direction of the gradient, right? Let's think about it from this perspective. You don't want to climb the hill. So a gradient is what? A measurement of the steepness of the surface. So you say, I don't want to climb it, so what am I going to do? I'm going to roll. I'm going to go with gravity, right? I'm gonna just roll with it, okay? This idea says if I go against whichever is the steepest direction, right? I set the value of, or update the value of the weight based upon my previous inference, my previous assessment of what the ideal value was, that I should be moving in the direction of greatest return on investment, right? The best mechanism for minimization of loss. We've said previously, a loss metric idea is that you lose something when you make an error, right? So it says, take the negative of the gradient, go in the opposite direction of the path of steepest descent, adjust the current value for the weight adjustment or weight assessment, adjust the coefficient of the regression in the direction as indicated by the opposite of the increase in error. That should be the maximum decrease in error, right? We're going exactly the opposite direction of the vector that was telling us that it would be the maximum increase in value, that we should be going towards the maximum decrease in error. That's a really cool function. That's a really cool capacity of these systems. Because effectively, the only thing that I need to know now is, how much do I move? How much do I move? I noticed something here. Initially, the gradient surface pointing this direction with relatively high intensity, because it's a pretty steep curve, right? How am I calculating this? Only based on the instantaneous characteristics of the error. What do I mean by instantaneous? Meaning I had an initial assessment, I adjusted it by some value. It literally does not matter how I adjusted it. Why? Because I'm still going to learn whether or not I'm going in the right direction, okay? So if I'm walking, if I'm here, and I spin around and then I take one step forward, it doesn't matter where I went to from where I was. I now know this is up, right? I say, hey, I was there, and now I'm here, I'm up. I say, I have to go that way, right? So I turn around and I go in exactly the opposite of the direction I went in. Now I'm going down, right? I should be traveling downward. If I'm not traveling downward, then I did one of two things. I either stepped too far, right? My step was too big, right? It implied that the steepness of the surface I was looking at was too steep where I was at and didn't consistently provide that same level of steepness, right? Or this little region of balance between the target value and adjustment in the slope of the line system is tighter than I thought it was, right? If you're trying to get down into the bottom of that hole, and that hole isn't very wide, right? It's like some gaps in the pavement you have to stop and jump over, right? Some gaps in the pavement, you have to, like, if you could just step over it, right? So this is a question of how wide it is. Is it a big pit that's going to be hard to miss? Or is it a narrow one that's going to be potentially easy to miss if you jump over it? So we started here, and I jumped, let's say I jumped all the way over here, right? I might entirely miss that this ditch happens, this ditch even occurs. So in higher dimensional, more complex spaces where you have multiple possibilities of this gradient surface occurring, you can entirely miss localized versions of the optimization, right? You could potentially miss the perfect balance between your parameters, all right? So I start off, I take all of the value of the gradient. I say, all right, I'm going to go exactly the opposite direction with as much gusto as I can, right? And I'm going to step over. I got over the other side of the system at W1, right? The second inference in the system. Say, well, yeah, I got better, but what? Now I can take the instantaneous gradient. I can say, what is the surface with respect to small differentials in all direction around that surface region? And now I can get a gradient that's indicating what? It says the maximum error is pointing in that direction. So am I going to continue to increase the value of the weight? No, I went too far, right? I went too far. I adjusted the value of the weight over too far. I went from here over to here, right? So it says, no, I'm going to go this way. So I'm going to jump over here, or excuse me, jump over here, right? My step size is still too big, okay? We call this step size learning rate. Learning rate is commensurate to how much of the gradient per given step I'm going to utilize as part of the adjustment for that weight value. The smaller it is, the longer it's going to take me to converge to a solution, right? If I take only tiny steps toward the wall, you know, like a geisha, you know, like it's going to take me a long time to get there, right? But if I take big, you know, Monty Python steps toward the wall, I'm going to get there quick, right? But what happens? I could have totally missed stuff along the way with the big steps, right? And I would have a much poorer understanding of the actual surface of the error. What do I mean by surface of the error, right? So we're looking at the simple version of the error surface. We've already seen optimizers. Error surface looks a lot like this one, right? You have some system where you have adjustments in the weights and biases relative to the error that are going to give you estimates of this function curve such that for specific values of the weights being adjusted in one direction, biases adjusted in another, you're going to have differences, high error in these positions where you have high biases, right, and relatively low weights, centering towards low weight and potentially a small bias in the offset as provided. Okay, this is a very simple version of an error surface with effectively a one-dimensional system. I say one-dimensional as a result of only having one weight really to adjust. But we still have two parameters. We have a weight and a bias to adjust here in order to try to find the best function approximation for this system. All right, so with the least mean squares gradient descent process, we're going to have these four calculations that are going to govern the mechanism of calculation for the estimation of error within the system. I'm going to calculate, first and foremost, some relationship between the current value, right? So this is the partial of JK, partial of the Jacobian with respect to the current value of that instantaneous gradient. And I'm going to say that that is related to the current value of maximum increase in the error function. Notice what's happening up top. I'm going to have W, that's my current value, or excuse me, WK, right? So let's look at inside, let's look at the right side first, right? What if right side first? Remember, sometimes if we work from the right back to the left, it'll make a little bit more sense. If I start at the left on this one, I'm going to say W of K plus 1. What does that mean? That's talking about the next step in the process, all right? So the current step in the process, what do I have? I have WK, that's the current weight. I'm going to take from it, why negative? Once again, because I'm subtracting what's over there on the right-hand side of it. I'm subtracting the gradient. But I have something in between the gradient and that minus sign. That's the scale of the gradient. That is effectively the learning rate. That's how much of the gradient I'm going to use every time that I update the weights, right? So noting the gradient is an estimation of how much that individual weight is contributing to the relative error performance of the system. I know that if I take it away, I take away the direction of greatest increase, that I should be generally moving in the direction of the greatest decrease in relative error. So by updating the weight at W of K plus 1, right, the next step of the process, the next guess, we start off with an initial inference, we calculate the gradient, we multiply the estimate of the gradient by a small amount of learning rate, how much of that total gradient I want to take with me, and then I subtract that from the current weight in order to get what's happening at the next value. This process can be recalculated using a substitution of error estimation within the system such that I can rewrite the estimation of instantaneous error as a result of the summation of the square error in the system for the instantaneous gradient estimation, such that I get 1/2 of the partial of the square of the estimation 4K relative to each individual weight, right? This is the argument of saying how much of the error does each weight own, right? How much or is it responsible for? Now, why is this challenging? Because we don't just have one weight. Matter of fact, we don't just have 2. We don't just have 10. We have hundreds, sometimes even thousands of them, right? They're spread across a system that has a feed-forward process, right? You've seen a lot of this stuff. Some of this stuff's in there just for refresher. Some of this stuff's in there because I made this slide for a general audience, right? But I'm gonna leave a lot of it in because I think it's good to be able to have it so that if you need it to review or if you wanna look at the full forms of the equations. There is one thing I wanna point out in this slide, and that is that for classification tasks, the loss function commonly used for approximation of error within the system, the loss due to misclassifications, is regulated as a double summation for the class indications and the kth indication of elements, right? So this is the elements and the class characteristics. So saying there is ith element in the system and there's kth class. So I must take into consideration an iteration forward through all of the n elements in the system and all of k classes for the classifier. But I end up with two things. I end up with yk log y hat k, right? So this is the product of the target and the inference, the log likelihood of the inference. And then I have what? The remainder for the likelihood class and non-class elements, right? The log of 1 minus everything that is the class. So this is saying that if I utilize the summation of the addition between the likelihood of being within the class and the likelihood of not being in the class, then I can determine the relative error via this, what we call cross entropy. The likelihood, how likely you are to be in it versus how likely you are to not be in it, should give you a good perspective, treating every class kind of independently, one to the rest, internally comparing with each other. All right? We've already seen playground, training processes. I'm going to skip forward quite a bit here because I have a better version of this model. Okay? This is what we call a feed-forward version of the network. We see calculations for it. Now we see feedback. This one runs kind of quick. I want to try to slow it down. I've been working on taking it and slowing it down. But I'm actually going to dump out of it and we're going to look at it real quick because I'm going to pause it toward the end of this system, right? So we know what happens very end here. We see what? We see an estimation of error at that local time, right? We have an error at the end of the system such that z, which is the output of the final activation function of F6, that sixth element within the network, as being a consequence of what? What is this error a consequence of? Well, it's an error, a consequence of the activation function partially, right? Or the biasing terms that are coming from F6 at the end of this process, right? That's one portion of the error, okay? We know that portion of the error, like we have that actual calculation of the output. So where else is it coming from? Anybody that led into it, right? Anybody that led into it made some inferences based on anybody that led into them. So the next contributor to error is going to be weights at the next step of the process. I have to wait for it to go all the way around every time, so just give me 1 second. I'm going to then do what? I'm going to assign some amount of error to the node that made the contribution to the final error of the system. I'm going to say, hey, here's all the error, right? I got a big basket of error. I'm going to say, here's yours, here's yours, here's yours, here's yours, right? I go around and I hand everybody their error, right? Why am I doing this? Why am I saying that you have some contribution to the error? Because everybody does, right? Everybody contributes to some level of error because what? You can't have non-zero error whenever you have systems that have true relationships, right? True mixed systems, okay? So I say it is possible to have a system with no error, but those are effectively toys, right? Things that we really wouldn't work with. You would never apply this to something that is totally linearly separable because, as I said beforehand, it's, you know, it'd be like trying to swat a gnat with Thor's hammer, okay? It's just way too much power for that particular task. You don't apply something that is easily solvable by a reduced methodology of complexity and higher complexity. It's antithetical to our mechanism. It's antithetical to that core process of Occam's razor, right? When all other things being equal, the solution that requires the least number of assumptions is likely the best solution. So I say the solution is the methodology for functional approximation. How many assumptions do I have? Each one of these weights is effectively an assumption. So I'm saying, based upon your assumption, this is how wrong you were. or this is your relative level of contribution to the total wrongness of the system, as this whole committee process provides a level of individual approximation error. So everybody's going to get one, all right? So we're going to walk through it again. First, we run through the example. Everybody makes their estimates, okay? Now everybody's going to get their error. Notice, it's being distributed around, so everybody gets their own version of the error. Now, since everybody has their own error delta, everybody has their part of the total error of the system. If I added together all those errors, I should end up with the total error of the system, right? How is it distributed? It's distributed based upon your weight. What level of significance your amount of contribution to the total system is being given, right? So if your vote has more weight, has more value, then I'm going to say your error, your contribution of error is greater, right? So if you want less contribution of error, maybe you need to crank your weight down. Maybe you're being too overzealous in finding your pattern, right? But I now have to determine something. So I said that every element of error at every individual node is due to what? The inputs times the weights that it's being given in the system. So how do I update this such that I minimize this? Okay? Note, if I minimize all of these, what should I also minimize? So if I can do the calculations such that I minimize the level of error for each individual weight relative to the amount of error that that particular node is being produced based upon what is called back propagation, right? So I first back propagated the error, and now I'm doing the weight update assessment. How am I doing it? This is a gradient function, estimation of instantaneous error based upon the input, and I'm going to then update the weight based upon that estimation of instantaneous error. Why is it now positive? Because the instantaneous error in this particular case has been modified to be negative, the opposite direction of value, right? Max increase error versus max increase value, right? D of E. The F contribution to E. This is a slightly different way of saying what we were looking at beforehand. But you can imagine there, instead of doing that negative nu times the partial or delta, right? Delta error times there is error with respect to each of the weight systems. Just say that's gradient J, that's the instantaneous gradient, right? So this new weight, the W prime, the weight at the next version, at the next inference, this whole network is going to have all of its weights updated based upon the assumption of how much each individual weight contributed by calculating the gradient of that weight's contribution to error as a result of that individual error at that node, which has been attributed to it via being propagated from the total error in the system. So once everybody gets their error passed out to it, everybody gets to adjust their inference to be able to maximize their contribution to the system. If everybody is making the maximum contribution towards being able to get the value of the system better, and we keep trying it over and over again, and we iteratively improve the estimate every single time, what should happen? The total error should reduce, the total propagated error should reduce, each one of the individual updates are going to be less and less to each of the weights, and eventually what will happen? There will be so little error that it will be very difficult to determine exactly who owns it. So over time, we're actually going to run into a little bit of a problem there at the end of the system. And that is, there's two problems here. What do we notice? We have reduced things based upon the scale of contribution. The relative importance of each individual error is relative to the relative contribution of the weight. So, if I calculate this from the perspective of saying that it is the derivative of the error with respect to that weight that's updating the weight system, if some of the error is here, right, and some of the error is here, and some of the error is in the next layer back, and some of the error is in the next layer back, how many layers do I go back before the amount of error, like delta 16 or something like that back in this system, is tiny, 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 tiny value, right? We go, wow, well, I know those weights contribute highly, and these weights contribute, and these weights contribute, but there's less and less error, effectively, less and less total percentage of error, that's coming back with you the further you propagate that error back, right? You go far enough back in the system, we call this the vanishing gradient problem. Meaning that the ability to distinguish who's responsible amongst a myriad of possible responsible individuals when the mechanism by which you're calculating their individual contributions is based upon the chain rule of calculus, right? So we're going to utilize the chain rule to determine the contribution of the partial of each one of these individual weights relative to the total error in the entire system. So the further back that chain goes, it is a less and less exact approximation of the individual contribution of error for any of those given weights. So each one of those error updates, each one of those guesses is going to be slightly less accurate with respect to who is truly responsible, right? You go, he did it, no, he did it, no, they did it, right? And it just keeps pushing back, and then you have like an entire room full of people, and they're all pointing at each other going, they did it, right? And you go, I don't know whose fault it is anymore, okay? Everybody's equally blamable, right? But who's really responsible? So everybody starts adjusting by tiny values, everybody starts sort of jittering around, trying to adjust based upon tiny decimals of derivatives based upon localized assessments. Eventually what will happen is you just can't change it anymore, right? There's nothing more that's really going to be valued back there. Or the value that you're changing it by just doesn't do anything useful with respect to that system. This is probably the most comprehensive way of looking at the entire flow process for neural network training. If you understand how all the math works here, you really got it, right? This is the entire workflow in a GIF. So if a picture is worth 1,000 words, then a GIF is worth 1,000,000. Technically, I could stand here all day, but if you watch this video over and over again, you'll get the picture, right, eventually. I can't really tell you how this works because there's not enough time, but if you really truly want to dig into it, get deep, there's some videos you can watch, really good stuff. Ray Blue and Brown does a really great job on explaining backprop. But the better you get at it, the more you understand exactly how this is being calculated, the more you get a feel for it. All right, so we'll talk about momentum next time, but I wanted to show you guys one real quick picture. This is a good example of what an actual error surface looks like, because we don't just have the relationship between the output of the system and the weight value relative to error. We have internal correlations and interdependencies between the weights. So as I adjust one weight relative to another weight, relative to the loss of the total system, I have weight 1 and weight 2, their values being adjusted with respect to one another. I end up somewhere there on that error surface. This is just two weights and one output loss function. What does this look like whenever you have hundreds of weights? No one has even the remotest idea, okay? We can't visualize it. You just get an intuitive feel for it that there is always a way to class or to structure this functionally so that you can understand it. In high dimensionality, in a system where you have less concrete understandings of the natural order of a system. Any of you guys ever seen or read Ender's Game? All right, the enemy's gate is down. That is the functional understanding that I've acquired with respect to what the gradient is about, right? The enemy's gate is in the opposite direction of the gradient, right? The negative gradient is down. Keep that in mind. Whichever direction is down in high dimensionality space, it's always the negative of the gradient. It's always the negative of the estimation of the instantaneous tangent based upon the surface. If you can get down, you can go down in however many dimensions you want at one time, and you can distribute which dimensions are responsible for the greatest amount of surface area error. There will always be a hyperdimensional surface that will indicate the direction of a specific vector, indicating the greatest reduction in total error of the system. It's fascinating and exciting, okay? We'll talk more about this on Friday, and we'll probably wrap it up. Thank you very much.
Thank you.
Thank you. Sure. Feel your hair blow back a little bit, trying to get through all this in short time? Yeah. Sometimes I feel like I blow through this stuff a little too